and so we are live. So good morning or good afternoon, depending on where you're joining us from, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are particularly excited because this is February, and February for us, in commemoration of February 11th, International Day of Women in STEM, means that we spend the entire month featuring only women. Over 45, 50 sessions from amazing women around the globe. It's our biggest month ever. It's our biggest month every year. And we're so thrilled to have you guys be a part of it. So right now we are joined by 4 classes from across North America. I'm gonna give them a chance to say hi before we dive in with our speaker. So we are joined by Miss Basaglia's grade 5, 6s in Maple Ridge in BC. Hi guys. They're so loud, they like half broke the mic. I love it. All right, we've got Miss Sharp's grade 12s in Parma in Michigan. Hi guys. Wow, that is actually, without a word of a lie, that's like the biggest yell from a grade 12 classroom I've ever had. So way to go to you guys. AP Chem for the win. All right, we've got Mrs. Philippone's class, grade 4, 5s in Mississauga, Ontario. Hi guys. Grade 12 classroom I've ever had. So way to go to you guys. Oh, they're on a delay. This keeps it exciting. All right, we've got Mrs. Philippone's class, grade 4, 5s in Mississauga, Ontario. Hi guys. Slight delay, but the enthusiasm's amazing. I love it. All right, and last but not least, right now we've got Miss Parrish's grade 6s in Petrolia, Ontario. Hi guys. These are pumped classes, Erica. I hope you're as excited as they are. All right, of course, the reason you guys are all joining us today is for our speaker. So we are joined live, not on some land, not on some boat, not even in a plane or on space. We are joined from 2 kilometers beneath the ground. So underneath Sudbury, Ontario, about 4 hours north of Toronto, for those who might not know, is one of the most elite research labs in the world in an active mine. And we got our 5th class joining us from Thunder Bay. Excellent. So 2 kilometers underneath the ground, they study particle physics. They study things about our universe, things like dark matter, neutrinos, some amazing, really cool science that's really unique. It's the only Erica is the only person that we bring in to feature this kind of work, so we're always excited to have her back. So Dr. Erica Caden is a research scientist at SNOLab, so the Sudbury Neutrino Observatory. I'm going to stop throwing all the acronyms at you because I'm stealing all her thunder. But without further ado, thank you so much for joining us, Erica, and take it away.
Thank you so much for that introduction, Jesse. So yes, I am underground right now. You can maybe see the walls behind me are a little uneven. So that is concrete that we've sprayed on the walls to keep the rock stable. And I'm just going to dive into my presentation if that's okay, because it'll make a little more sense explaining everything.
Let's do it.
So let me, wait, I can share my screen. I know how to do this.
We can solve major science challenges, but can we figure out Zoom together? I bet we can.
I think we can. Play.
Cool.
Okay. Oh, I go all the way to the beginning.
Oh, close your eyes. There you go. Perfect.
There we are. So my name is Dr. Erica Caden, and yes, I'm a research scientist here at SNOLab. So this means that not only do I sit in front of a computer all day, I get to tinker with electronics. I get to hold comically large wrenches. Oh, and the picture on the bottom, I am working with another faculty scientist from the University of Alberta, and we are looking for deformations in the wall of the cavity in our experiment. So it looks like I'm in a big inflatable fishing raft because I'm in a big inflatable fishing raft because surrounding our detector is a bunch of water. But I'll talk a little bit about this later. But I really like to show these pictures to show all the different things that a scientist does. We don't just play with chemicals. We don't just sit in front of a computer. There are a million different things that we do every day on our experiments. So here is a picture of the surface building at SNOLab, and this is about what it looks like right now. We've got quite a lot of snow up here in Sudbury. And you can see in the map inset where the little purple pin is where we are located. I'm sorry to have cut off a bit more of Canada and not represent some of the places where the classrooms are here today. But it's we're 4 hours north of Toronto, and we're in an active nickel mine. So the Creighton Mine has been running for over 100 years. Sudbury is known as the Nickel City. So we are in one of the number 9 shaft, which just means the tube or the hole going down is where our elevator runs. All of the red is the ore body, so where they are getting the nickel from. We get off at the 6,800 foot level, so that is just a hair over 2 kilometers or 1.25 miles straight underground. The cage ride today was no stops, full speed. It took us about 4 minutes to get from surface to a mile underground. And if you walk then another 1.5 kilometers or so, you get to SNOLab. So this is this inset in the map in here. So we're about the size of a shopping mall. Oh, excuse me, our PA system. We're about the size of a shopping mall here, 5,000 square meters or 54,000 square feet of space. There are over 10 experiments either running or under construction, studying neutrinos and dark matter, which is, would kind of make up astroparticle physics, understanding what makes up the universe around us. But we also have 2 biology experiments that I'm a little less familiar with, but they take advantage of the ultra clean facility we have that is ultra low in cosmic radiation and in these higher pressures that we have underground. If you've ever been in an airplane and you feel your ears pop, it's because there's less pressure around you. When we go underground, there's more pressure around you. So they can use that to study some aspects of genomics and microbiology, which is really interesting to do in an otherwise physics lab where we study, again, neutrinos and dark matter. So what are neutrinos and dark matter? They are unfortunately not little plushies that you can get and carry around and snuggle with from the particle zoo. They are subatomic particles. So the smallest bits of matter that we know, that we understand. They are mysterious in that they are difficult to detect. So we have to build very big, very sensitive experiments to try and see the little signatures of light that these particles leave when they interact. And dark matter is even more mysterious because we haven't yet observed dark matter. We can see its effects when we look out in the sky. We can see how light is bent by dark matter, and we can see how it holds galaxies together as they're spinning around, but we don't know yet what the dark matter particle is. So we find that really exciting as scientists, that we have an idea of what we're looking for, but we don't know yet. We're really trying to understand the unknown with the experiments that we have here at the lab. So one of the interesting things that I find is what we can use neutrinos. I work more on the neutrino experiments, what we can use them to learn about the world and where they come from. So in my experiment, we study, which is called SNO+, and I'll show you really pretty pictures of that. We study neutrinos from the sun, which happen in the fusion process naturally in the sun. We study neutrinos from fission, from the nuclear reactors, and there's a few in Southern Ontario that are close enough for us to see the neutrinos that are produced from normal fission reactions, and from things called beta decay, which is just a normal natural decay process from the elements inside the Earth, but we can detect what are the fraction of elements inside the Earth from the neutrinos that they emit. So that's a really great way to kind of compete with the geologists who are studying the Earth and rocks, and we can do that with particle physics too. So the neutrinos, the questions that we're looking to answer by studying neutrinos are about kind of all of those sources. What makes the Earth so hot? Why are we're not just warm because of the sun, although we can also use neutrinos to study the sun. We can understand how elements are formed during the fusion process, and we can study how stars explode, how supernova happen, and even how the heavy elements are formed from the supernova explosions. And we can do all of this with these little humble neutrinos. So this is a picture of the experiment that I work on. It's called SNO+. It is the successor, the second experiment to use the hardware that the original SNO experiment used. And so the leader of the SNO experiment, Dr. Art McDonald, was one of the co-winners of the Nobel Prize in Physics in 2015. So this is the experiment that he helped lead, and now I get to be a part of. This big sphere is 18 meters in diameter. So it's huge. I guess you can see the people on the bottom here. It is so this is the outside of it, And all the little white dots are sensitive photo detectors. So they can detect tiny, tiny, tiny amounts of light that are produced when particles pass right through it. And it used to be filled with water, and it looks like this. So this is a picture from a camera that we have mounted inside the detector. So you can see all of these lines are ropes that are holding the central sphere up and down. And all of the dots on the inside, all of the small circles, are the front faces of those light sensors. And so we have an electron neutrino and electron antineutrino plushie kind of show what those are the particles we're looking for in our interactions. So this is how it looked when it was filled with water. But right now, this is how it looks as a picture taken just last month. We are currently draining out the water from the bottom and filling it with a special mineral oil that will let us see neutrinos of even lower energies and different neutrino interactions. So we can keep studying and keep trying to understand all the world around us with different precisions. So this is a very exciting time right now to work on this project. But also at SNOLab, we have even more experiments studying dark matter. So here's on the left is a picture of what's called the Deep 3600 detector. So all of those little dots are also the photosensors, and it uses liquid argon to look for a dark matter particle bouncing off a nucleus of argon, and argon is 1% of the air around us. And the picture on the right is the PICO detector. So they use a superheated liquid and looking for bubbles that are produced when the dark matter particle interacts in the detector. So we have many different ways of studying neutrinos and dark matter at SNOLab, and we have so many questions still about them. So now I am going to stop talking and let you guys ask your questions of me about anything that I've just said or anything about the lab.
Or comically large wrenches. I mean, like,
or comically large wrenches.
Really cover that at some point in one of our sessions together. Erica, thank you so much. What a fantastic presentation again, diving in. So in addition to our 6 live classes, we've got at least 4 more watching on YouTube. So if you guys want to type questions in the chat bar, please do. Only for classes, please. So do let us know what you're interested in, and I'll share as many as I can with Erica. But with that said, let's begin by going to Maple Ridge, BC, Ms. Pisaglia's class. You guys want to kick us off with a question? Come on up.
Just say it. Okay.
Don't be shy, all good.
My name's Cohen. What's the temperature down there?
Okay, so that's a really good question, because as you saw, it's snowy outside, but deep underground, it's really warm. The rock just gives off heat from all of the particle decays inside it. So whenever you have freshly mined out ore, it's warm. It's about 40 degrees Celsius in the air, which is about 80 degrees Fahrenheit, 85, I think. So it's warm underground. And a lot of the work and the engineering in the mine is to mitigate that heat. So it's not as hot for the miners to work, because the deeper down you go, the hotter it gets. So they have to really control all the airflow through the mine to make it comfortable and safe for the miners to work. Now, luckily in the lab itself, it's a little bit cooler. We keep it at around 21 or so degrees Celsius, so a nice room temperature. But unfortunately, that's because the computers need that to work properly. We have all of the computers collecting data for all of the experiments and all of the big servers for the computers. So it's lucky that we like to operate at that temperature too, because we need it for the experiments and the computers.
Very cool. So if the computers needed like 150 degrees Celsius, you guys would just be SOL outside the lab. No,
yes.
No opportunities. Fantastic, guys. Let's go to Miss Sharp's class. If you guys want to come up with a question, go for it. Oh, I had you unmuted, and now it's not letting me. So Miss Sharp, just demute your mic, and then we'll be able to take a question. I'll let you know when it's good. It doesn't like me anymore. There you go.
I thought I was one step ahead of you. There we go. This is Beth.
Oh, hi.
Hi.
So I have a question. How many gallons of water or mineral oil does it take to fill the snow reactor?
Yeah.
So when we were filled with when it was just water, it was 980 tons of water. So I don't know how many gallons are in a ton, but it's a lot. So a ton is like a cubic meter. But the scintillator, the mineral oil, is lighter than water. So that is only 780 tons of weight for the same volume. So this provides an interesting challenge for the experiment because surrounding it is all water as well. And we all know that oil floats on water. So when the detector is filled with mineral oil, there is a buoyant force pushing it up because it doesn't want to stay hanging in the water. So we had to engineer a whole net of ropes and anchor them into the ground in the cavern to keep the detector steady where it is. We had to figure out how much that buoyant force was going to be and how much force we needed the ropes to pull down and have safety factors in there so that the oil doesn't make the detector crash through the ceiling.
Which would really suck.
We've got only one of them.
Yeah. See, if you're ever bored in math class, you get to do stuff like this if you stick with it long enough. Mr. Classon's group on YouTube, so they're from Pruder Public School in Kitchener, Ontario. A lot of Ontario groups on YouTube today. How often do you go home, or do you stay in the lab longer than a day?
So that's actually, I try to go underground once a week or so. But everyone goes home at the end of the day, certainly for safety reasons, also because we like to have lives outside of doing science. But there are operations underground just about 24 hours a day, also for the mining, but for the science as well. The process plants that we operate to fill our detector with liquid, they take a long time to turn on, so we need to keep them running as well as possible for as long as possible. So once we start on Monday, there's rotating shifts until the end of the workday on Friday.
Fantastic. All right, Ms. Philippone's class, with our first ever question being asked in an Exploring by the Seat of Your Pants session.
Until the end
Now
of the
they're on a delay. Okay. Well, we'll get them when they come in a second. Ms. Philippone's group, you're up. Hey.
Hi.
Yeah, ask a question, guys.
Yeah,
Yeah. Yeah, ask a question, guys.
go ahead.
Do you have Wi-Fi down there?
Yes, we do. So that's a relatively new thing. We didn't have Wi-Fi for a long time, and I'm actually on it now because I forgot my cable, so I hope it is strong enough. Sometimes I like to walk around a little bit with my laptop, but I don't think I want to test it right now. I can maybe show you guys. So this is the door that we enter, and the thing that looks like a closet is actually called an air shower, and it sprays jets of air on you to wash off any dust that has landed on you just from being in the air. Oh, so a thing I didn't mention yet, which is super exciting about SNOLab, is the showers. So we are an ultra clean facility. I think I might have said that. That means there's less than 2,000 pieces of dust in the air that are larger than half a micron in size in a cubic foot. So a little awkward to mix all of the units, but it means that we are essentially as clean as an operating room, but we're inside an active mine that's dirty, and you walk through this dusty, windy tunnel to get here. So once you get into the lab area, you have to take a shower. You have to wash all of that dust off of you so you don't contaminate the experiments, because that dust would create signals that aren't the things that we're looking for inside our detectors. So we have to take a shower and wash our hair and wash our skin. And you might see I've got a lovely hairnet on. This is to help keep all of our experiments clean. So the air shower is just another step to keep the experiments clean. And those blue doors are on the way to the deck to where my experiment is. The big blue ball is just right over there.
Outstanding. I'm really glad we got the ultra clean definition in there. All right, I'm going to go to Ms. Parrish's group. If you guys have a question, come on up.
When did you guys start building your underground base?
Yeah.
Oh, so the construction for the original SNO experiment started in the mid to late 1980s, and that started taking data in around the year 1999. And by the mid 2000s, around 2004, 2005, they started expanding the lab. So it was just a one experiment. And then they expanded, they dug out more and expanded the size of the lab to host a bunch more experiments, because the whole science community realized the facility that we had here and all of the work that we've gone into developing the procedures to keep it clean and to do great science here. So everybody kind of wanted a corner to build their experiments, and we ran out of corners. So we had to build the whole lab and expand it dramatically. So now we have 3 big caverns that hold lots of experiments. And that finished construction in like 2012.
Okay, so not that long ago. Can I say too that the language used in that question was amazing? Can we always just call it your base and make you sound
The
like
underground base, yes.
Yeah, with the lava tube to the secret layer. All right, I'm going to take a quick YouTube question. Mr. N's group, Kelowna Secondary School, wanted to ask, when will your experiment be concluded, Erica?
Oh, so that is also interesting because we have multiple phases of our experiment. So once we finish putting the mineral oil in, then we will put in another element called tellurium-130. And it is one of the ones that's in the bottom of the periodic table that you don't really get to a lot in chemistry class, except the high school chemistry class. Maybe you guys know about tellurium. We will put that in our detector, and we will look for a rare nuclear process called double beta decay. And we're going to try to make some measurements of that, which can tell us a lot about the neutrino that other experiments or other phases of our own experiment can't tell us. And we'll be looking with other experiments for some of these interesting properties about neutrinos that we're still trying to understand. And so that will start our 3rd phase. Sorry. That will start the last phase of the experiment, but maybe depending on how that goes, if we can put more tellurium inside, we can keep doing interesting science. So we will want to run for probably 6 or 7 more years. But that's not necessarily the end of the experiment. We can keep doing more. And that's one of the interesting things about a lot of these projects is we have our timelines that we want to, for our initial results that we want to get out. But then if we can expand and do more and we can get more money to do more, then we just want to keep doing more. By having this facility, we want to make the most out of this facility.
Yeah, amazing. All right, another quick YouTube question because it's easy from Miss Laser's grade 4 or 5 classes in Thornhill. They wanted to ask, how do you breathe down there?
How do I breathe?
Yeah.
So they have air that flows. So we talked a little bit about how hot it is and the cooling that they have to do to keep it safe for the miners to work. The airflow also comes into the lab. So that's one of the big things about the lab is the cooling capacity and how we can keep it comfortable for the experiments. We circulate the air around the lab. The whole volume of air is exchanged 10 times every hour. So that helps keep the dust down, and we run it through our chillers to keep it at the right temperature. So they just pump air in from the surface. And there's big fans that do it.
All right, let's go to Miss Lang's class in Thunder Bay. If you guys have one, come on up.
How do you know dark matter exists?
Ooh, good question.
So we can see the effects of dark matter. We can see how giant galaxies spinning around, the stars and systems at the outside of the galaxies are still attracted enough to something in the center of the galaxy that they don't fly off. So we know that there's some attractive force in the center of the galaxy that keeps things together. We can also see light bending around what looks like nothing because we don't see it, but we can see how stars that should be like lines, galaxies from edge on, are slightly bent. Like if my face was dark matter, this is how it would look because the light is bent around them because it has a gravitational force on the light, on the photons that are coming from, on the space-time that's coming, the light that's coming from the galaxies behind the dark matter sources. So we can see the effects of dark matter. We just don't know what it is yet. We're really good so far at not finding dark matter. We have this parameter space of if the dark matter particle is a certain size and if it has certain probability of interaction, we ruled out like all of this bit of it. We have all of these experimental results that say if there was a dark matter particle that interacted this much and was this size, we would see it, but we don't. So we know that it's not here. And so we just keep carving out little chunks of this, we call it parameter space, this of what we think we're looking for. So there's just a couple areas left that we haven't found yet, or that we haven't yet been able to search because we haven't built detectors sensitive enough. So that is one of the challenges that we have, is building better detectors, but then also thinking of different ideas. If maybe we're wrong about the way that we're searching for dark matter, we have to come up with different ideas to look for it because we're pretty sure it exists.
Fantastic, Erica. And again, every time we get that question, it's such a complicated science. There's so much behind it, so it's difficult to convey in about a minute. That's about as good as you'll get, guys. That's fantastic. Let's dive back in with a full round of questions from our live classes. So Ms. Pasaglia's class, if you guys want to come back up, go for it.
Sure you crouch down in front of you.
Are you ever scared down there, like underground?
Yeah, so there have been a couple experiences that have been maybe not scary, just a little unnerving sometimes when we are, I guess it's not scary because we rely on all of the safety equipment that has been tested and engineered and all of the safety procedures that have been developed to keep miners safe for hundreds of years here in Canada. So when something happens in the mine, they stop all the work and everyone just kind of sits and waits calmly until they have fixed some other problem, so that even if there's not like a big problem, even if they're just doing some work on the elevator, it's the only way in and out of the mine is the elevator. So if they just need to do some routine work, they make sure that everyone's on the elevator. They make sure that everyone stops their own work that they're doing so that no one has any possibility of getting hurt, because they know that they can't come rescue us. And mine rescue is a whole separate field and an amazing work of people to get, not only to do their normal work mining training, but also to do the safety and rescue training to come and save their fellow miners if something happens. So to prevent having to do mine rescue, everyone stops their work when work on the elevator has to be done, so that there's no possibility of getting into an accident. And we all have lots of training and all of these different safety procedures, and that's all regulated by the Ministry of Labor and the Ministry of Mining. And it's a very safe feeling to be here, actually. That's a great question. Thank you.
Yeah, I always love when we get that one. All right, Ms. Sharp's class, if you guys want to come back up again, go for it. Let's just get your mic on again. Again, it hates me today. There we go. Perfect.
Hi there. Hi. My question was, did you always know you wanted to do something with dark matter? And if so, where did you go to study this?
These are the questions I get from the older classes, which are great. I knew, I think sometime in grade 11, grade 12, that I wanted to be a scientist. And I wasn't exactly sure what that meant, but I knew I liked science classes because I liked not knowing things. I liked being challenged and I liked really having to figure things out. So I'm from the States. I'm from Philadelphia, or just outside Philadelphia, New Jersey. So I went to a small liberal arts state school that had a decent physics program and studied physics there. And I knew kind of maybe towards the end in my third year that maybe research was what I wanted to get into, that I still really liked answering questions and I liked learning. I didn't want to stop learning. I didn't want to just get a job. So I realized I wanted the grad school, that going on and getting my bachelor's was the right path for me. And I went to graduate school at Drexel University in Philadelphia. My undergrad was called the College of New Jersey outside of Trenton. And in grad school was when I learned about neutrinos and learned about about public speaking and about kind of the outreach things. So it's not just doing science, but it's talking about science too. And where I learned about neutrinos and doing research in the projects, all of the different experiments that there were, and all of the questions that we still had about neutrinos and dark matter. And so I was in grad school for 8 years. It was a little bit of a long time, but I got to work on every different part of my experiment. And the project I worked on was in France. So I learned that I like to travel a lot too. And then from that, I realized that I wanted to be on site for my next experiment. So then I came up here to Sudbury, Ontario, and I worked at Laurentian University for a few years before I started at SNOLab.
Amazing. Thanks, Erica. What a great story. I love when we can hear the background of scientists and how very, very different they are. Almost every one of our sessions has that question come into it, and it's really interesting and unique to hear that personal tale. So thanks. We've got 3 more live questions. I want to take one from a group online because I love when we get this question. So Mr. N's class, again, Kelowna Secondary School, wanted to ask, how much does SNOLab cost and who pays for it?
The operating costs are, I don't know the number off of my head, and I don't want to get in trouble for saying the wrong one, but it is paid for by the initial grants was federal and provincial money. And so our operating costs are through the Canada Foundation for Innovation, the CFI, and we're a major science initiative for them. So we have about 120 people that are employed by the lab that are employees proper, but we also have visiting scientists from all of the experiments on site almost all of the time. And so those are from all over the world. So different universities in Canada, universities in the States. We have collaborators in Mexico, all over Europe. We have people coming to visit to work on their different experiments. So all of the experiments here are kind of largish collaborations. So the big accelerator that's in Switzerland, CERN, those collaborations are thousands of people. Those are mega groups. Ours are generally between 50 and 150 people to work on each of the projects, and people work on multiple projects. So I work on SNO+ that I showed, but 2 other neutrino experiments, HALO, which is dedicated to looking for supernovas, and NEXA, which will also be looking for that rare neutrino process called double beta decay.
Yeah. And I love that question. And so I'm going to come to Miss Philippone's class next. I know there's a bit of a delay, so just get ready for a question. But while I'm waiting for that, I just want to highlight, whenever it comes to space or physics question sessions, we always get this question of how much does it cost? And these are expensive scientific endeavors, but really, if you look at the scheme of things of the total percentage of the budget, I mean, even NASA in the States, which is arguably the most well-funded science organization in the world, is like 4/10 of 1 penny on the dollar. And you get all the rovers, all the staff, all the developments, all the scientific advances because of that. And that's similar to what we're getting with things like SNOLab. Like, these are remarkable organizations and institutions doing work that's not just producing Nobel Prizes, and but is really like spearheading huge new fields of science. So I'm really glad we get that question, and I love it.
One of the things that we like to say that we do is not just, again, produce science like you said, but we produce scientists. And a lot of our focus is on training young scientists, students who come up to work for summer terms, for co-op terms, and get to really learn the scientific process and get to put their mark on these big projects and come out of here with different skills. So you might not be a scientist when, like, as the way that I'm a scientist, when you leave science. You might be a data analyst, you might be a developer, you might be a coder, you might have you might work on Wall Street, you might do a million different things with the skills that you learned in science. So that's really one of the things that we like to focus on. And by bringing people here, the money that the government spends on the facility creates the revenue of many dollars in the local community for people who stay here and then go out to eat here and decide to make their home here, like I did.
Yeah, outstanding. All right, Miss Philippone's class, if you guys are ready for a question, come on up.
Why is the SNO lab so clean?
Yeah.
So it's so clean because the dust would contaminate our experiments. So the dust all around us contains little bits of radioactivity, things that aren't harmful to people whatsoever. but the detectors that we have built need to be so sensitive to see the tiny interactions that we're looking for. The dust would produce a signal that mimics those interactions. So we need to eliminate it as much as possible, so that we only see the things that we're looking for. So we come 2 kilometers underground to prevent reactions from cosmic rays. The just normal particular interaction in the sky would make a lot of noise, a lot of signal inside our detectors. So 2 kilometers of Earth shields all of that away. But then we have to make sure that we don't add extra noise in our detectors from the dust. And we have to make sure that our detectors that are made out of ultra clean materials, so that we don't create our own backgrounds, our own false signals inside the detectors, and that we're only seeing the particle interactions that we're looking for.
Try and envision, if you can, examples where you try and find the tiniest little signal. Imagine if someone lit a match on the moon and you were trying to see that match. It will be impossible to us, but detectors like SNOLab are able to pick up those sort of signals. Or if you're on the other side of a football stadium and someone was whispering to you, you'd have to try and hear that, and the detectors there can hear that. But if anyone else is yelling near you, you'd have no ability to hear that whatsoever. So if we get rid of the dust, we avoid all those hypothetical yelling people, if that's an okay analogy.
Exactly, yes.
All right. Let's go back to Miss Parrish's class, one of our last 3 questions, and come on up, guys.
How big is the lab that you're working in right now?
So it's 5,000 square meters in area, which is about 54,000 square feet. We have a shopping mall in Sudbury, and we are the same volume as the shopping mall. So, but of that area, there's 3 giant caverns. So, and they are all like 30 meters high by like 25 meters wide, and they're kind of cylindrical or kind of box shaped. So those hold some large experiments. But we even have some experiments here that what we call tabletop, which is maybe doesn't fit on a normal table, but it doesn't take a giant cavern. And we can have more of these smaller experiments too.
Yeah, how neat is that? All right, a question from a YouTube group before we wrap up with Ms. Lang's class. The question from a variety of students typing in was, what's the most interesting thing you've learned or seen on your job?
Oh my goodness.
No pressure.
Most interesting thing that I've learned on scene. So this will actually, it's not this job specifically, but going back to in graduate school, the experiment that I was working on was looking for a tiny number. So most of these experiments are looking for small numbers. So we didn't know if that number was 0 or if it was just really close to 0. There was a limit before, so we knew it was less than like 0.2, I think. But we didn't know when we were building the experiment if we were going to be searching for a number that was actually 0, and we wouldn't be able to measure 0. We would just get closer and closer and closer and closer and spend more and more and more money on all of these experiments trying to measure a number that theory told us might be 0. So it was a really interesting philosophical thing to think about, that how hard are we going to work to try and measure 0? And it turns out that it wasn't 0, that we actually have a number, so we could update all of our understanding of how neutrinos move when they move through space. But the idea of how much time are we going to spend trying to measure something that's actually 0, not knowing if it's going to be 0, was a really interesting thought to have for their first few years of grad school. Yeah. Of what are we doing? So that's one of the interesting things, is then finding out that we're not measuring 0. Yeah, that's a good question. Thanks.
It's a good question. It's a hard question to answer in a minute, so well done. All right, we'll wrap up with one last question from Ms. Lang's class. If you guys want to come up.
What is the biggest discovery made at SNOLab?
So that is an easy question so far. The biggest discovery that's been made at SNOLab was that neutrinos oscillate. So this is also maybe a little hard to explain very quickly, but neutrinos, what a neutrino sees itself, when a neutrino looks in the mirror, it sees a certain flavor, a certain kind. So imagine, let's forget neutrinos and think about birds. Imagine that you're a bird and you're a parrot, and you're a beautiful parrot, and you're flying through space, and you look down again, and all of a sudden you're not a parrot, you're a bald eagle. You're like, awesome, bald eagles are great. Sorry, American again. But you keep flying, you're like, I'm a bald eagle, and you look down again, and you've turned into a flamingo. So you are still a bird this whole time that you're flying. But what you look like, what you're interacting as, from a parrot to a bald eagle to a flamingo, changes as you travel through space. So if you are a scientist and you only have a flamingo detector, you're not going to detect this bird when it is a bald eagle or when it's a parrot. You only detect flamingos. So the SNO experiment made this measurement of trying to understand how neutrinos interact. And essentially, they made a detector that was sensitive not just to flamingos, but to flamingos and bald eagles and parrots. And maybe my analogy is going a little off the rails, but because of this this detector that could detect neutrinos in different ways, they were able to understand how neutrinos from the sun oscillated. So that's what the Nobel Prize was awarded for, with another experiment in Japan who made a similar measurement, but with neutrinos from a different source. So we knew that atmospheric neutrinos oscillated or changed, the bird changed what kind of bird it was, and that solar neutrinos did the same thing. So that is definitely by far the biggest result that's come out of SNOLab. And that was before it even, those results came out before the lab expanded into the full facility. Yeah. Hopefully in a few years, I'll be able to tell you that we've discovered dark matter at SNOLab too. But I don't want to count my birds before they hatch.
We reserve the right to be the first e-learning program that works with you after you've won the Nobel Prize, if that happens. Also, I'd love to see an actual flamingo detector. We should talk to a bird scientist. And finally, just a quick note that Canada actually has 10 times the bald eagles of the US, so don't worry, we know. Before we wrap up, Erica, again, fantastic. And I know it's difficult conveying some of this stuff and some great questions today, really detailed questions. Where can we send kids to learn more about SNOLab and the work that you do?
You can go to SNOLab.ca. We have a virtual tour of the lab. So a series of cameras that were set up and big 3D photographs that were taken that you can walk through the lab. I think we might have some of the links to previous questionnaires that we've done here with Exploring by the Seat of Your Pants with you and Joe. But SNOLab.ca is where you can find out everything about the different experiments in the lab.
Amazing. So I'll share that with all the classes when we're done. And for new classes joining for the first time, you might not know this. Erica, you will, because you've done like 10 with us. But what we do at the end of every session is I'm going to demute every class's microphones, the ones that I can anyway. And if you guys could join me in saying a huge thank you to Erica for joining us today. You are all now demuted. Go for it. What? You guys ran out of steam at the one yelling. That was fantastic. I love it. Thanks to all our classes for joining today. Again, we really appreciate you guys coming in February, our whole month dedicated to women in STEM. So please do come back for more sessions throughout the month. Dr. Caden, thanks so much for joining us again.
Thank you, Jesse.
All right. Have a wonderful rest of your day now.